Okay, so the focus of this class exercise is the Catalan numbers. And it will be shorter than the usual, and towards the end of the class, I'll talk a little bit about, I'll just mention it now, I'll talk a little bit about free groups and about K-graphs. But I will do so, I only do the bare minimum, which is going to be needed for you to solve the homework that I'm going to publish today. So this is not going to be the focus on the exercise. Mostly we'll talk about the Catalan numbers and their generalizations. So the Catalan numbers can be defined in few ways. I will choose the recursive way first because this will be more useful to us. And they are defined as the following recursive sequence. So I have C0, okay, I denote them by Cn, Catalan numbers. And we have C0 equals C1 equals 1. That's the base of the definition. And I write the number Cn as the sum over I goes from 1 to n. I'll make sure in a minute that I got this correctly. That this is C I minus 1 times C n minus I. Pretty sure I got this right. Yes, and this is for n greater or equal. Now, these numbers can represent a lot of combinatorial objects. Like many counting, they naturally occur in many counting problems. So I'll mention a few and talk about some of them. So one we've already seen in the lecture today is the number of Dyke paths of length 2n. Another one is the legal sequences of parentheses parentheses in plural is parentheses. I'm not sure. Legal sequences of parentheses of length 2n. It is also the number of, I'll write it down and then explain, non-crossing partitions of length n, length or yes, set size n. I'll explain what I mean here. If I have a sequence of objects, the order matters here, and I want to partition them. Just a partition, I can say, okay, I can have the green elements as one part in the partition and the others as the other part. And what I want to know is whether I can or I can draw a line below there can be a formal definition with the indices. It's easier to do it as a drawing. So if I can draw a line below each set, so this is one set in the partition and the other part is this one. So I ask whether I can draw such lines in a way that the lines of both of all the parts don't cross. So this one is actually a crossing function, it's not good. But another one, let's have the same green one is one part. this would be a part of its own. So in this case, this is a good one because I can draw the lines below the partition like this. Okay, this on its own. Okay, so this is a crossing partition, and this is a non-crossing partition. Right, it's good. Okay, so the number of non-crossing partitions of length n is also represented by the Catalan numbers. Any number? Yes, any number. Yeah, you don't care how many parts, but it has to be a partition. Okay, there's always the trivial one where they're okay. And another, say, combinatorial class of objects that are counted by the Catalan numbers are the number of binary trees with n plus 1 leaves. And this one I'm actually going to prove now. To prove that this is represented by this sequence of numbers. Okay, you may have probably seen a few of those, or probably not all of them, but and maybe other objects as well. I will prove it for the trees, and then we'll see what else we can say. Okay, so how do I prove that the number of binary trees with n plus 1 leaves is represented by these numbers? First of all, I need to check the base case, and then I need to be able to express this counting problem as this recurrence relation. It's like ordered. So, okay, thank you. So let's say this tree, this is a binary tree, and this tree, binary tree, and they are different. Okay, it's important. Yes, thank you. Okay, although they are isomorphic, but it's not the same. Not the same. Okay, so first of all, let's check the base case. So let's say T0, the number of binary trees with one leaf. So this is just this graph, right? With only one node, which is a leaf. T1. So this is one. Yeah, I'll change the definition in a minute to something that I'm more convenient with. But otherwise, it would. In the other definition, it's even weirder. And if I need to have two leaves and I need to have a binary tree, my only option is to like that. I denote the leaves and the full. Okay, so there's only one of those. This fits the definition. And now I want to be able to write down a recursive relation. So let's think about binary trees. So then there's two which may be leaves and may not be. And I can write, let's say this is P, and right here, let's say PA and PB for both its children. I want to express the number of leaves in each one in a way that will make this one be of size of n plus 1 leaves. And now I'll do something tiny bit different. Instead of writing n plus 1 leaves, I'll write n internal nodes and non-leaves, which is pretty much the same. Now here I have one internal node. We already know that this is not a leaf. And let's say this one has j internal nodes. So overall, I want to have n internal nodes, and there's already one here. And let's say this has j internal nodes. So here I'm bound to have n minus j minus 1 nodes. It didn't write anything here. But this tells us that the expression of Tn can be written as some, I didn't put any restriction on j. This can be a leaf, so j can be 0, but it can also be anything up to n minus 1, right? For this to make sense. So this is j goes from 0 to n minus 1 of all the options I have to construct. So first of all, I decide how many internal nodes are here and how many are here. And afterwards, I say, okay, after I decided that, how many options do I have for the left part? So it's tj times t n minus j minus. I want to prove it. Okay. Yeah. And from here to here is just the changing of the variable name from j to I, right? I will equal j plus 1, and this is okay. Now, so I proved that this satisfies this recurrence relation, and so for every n, n equals n. But I need to say, okay, what this number is. Like giving a recursive relation is not typically something that's good enough for us for solving anything. We want numbers. Now, I first want to say in some places the Catalan numbers are defined as their actual formula, which is 1 over plus 1 when choose n. And now this requires a proof. I need to prove that the numbers satisfying this also satisfy this property. And note that I don't have to count separately each one of those. I can pick the problem that I'm most convenient with, assuming for all of them I was able to show that they satisfy this recurrence relation. Once I do that, it's enough to count one of them, prove that this is its formula to be convinced that this is the solution for all of them. And we do this, and I put, probably most of you or all of you have seen it before. I put a guidance to how to prove this in the homework that I'm going to publish today, and this will be using the like paths. You probably have seen something similar, and this is not obligatory. You don't have to hand this exercise, but for completeness purposes, I put it in. And note that for some of these problems, showing directly that counting them is the same is not very easy. So for example, showing that the number of Dyke paths and the number of legal sequences of parentheses, showing that these are, you can write a bijection between the two of them is very easy. It's pretty immediate how you translate uniquely a Dyke path to a sequence of parentheses. But doing this bijection, obviously they have the same count, and these are finite objects. So there clearly is a bijection, but showing this bijection is not easy at all. But showing that both of them satisfy this recurrence relation is pretty easy, pretty similar to what I just did with the binary trees. Okay, so the fact that several problems are all counted with the Catalan numbers doesn't mean that they look the same. And sometimes, and we'll talk about it a little more later when I talk about generalizations, sometimes it's not quite clear when you look at the problem if you're not familiar with it in advance, knowing that it's going to result in the Catalan numbers. I mean, in these two, if you know one of them, it's pretty easy to translate to the other. With this one, maybe not. Okay, questions so far? Before I get to more tricky parts? Which one should I do first? Okay, so let's write thing down as an exercise.
He's doing the Check.
I'm not doing it.
The slides are on.
Okay, so let's define a function. Define a function that I call g of z. May look familiar to you, but I just call it g of z. Don't mention anything else. And I define it as sum over n goes from 0 to infinity of the Catalan number divided by z to the 2n plus 1. Now this may look familiar from something you've seen in the lecture, but we don't need the definition of any other thing that is denoted by the letter G. And what I want to prove that these prove that, say, for large enough G, for large enough Z, G of Z equals, and I want to express this infinite, this power series as a function. It's f of, write it properly, a minus 1. Okay. Now, it's not clear when looking at it how do we even start. But so I'll say a couple of things about it. First of all,
It was fine. Choose
oh right. So I can define Z to be either in the complex time or in the reals, but starting from I'd say for large enough Z, I mean large enough real value.
Wait, I'm just saying, this today is like confidence, or this is loud enough you can.
Right. Yeah. That should be this to be convergent at any point, we need to claim that the numbers are bounded. And it can be, and it's clear from the definition or from any of the problems I stated here, it is clear that, let's say you can bound it really roughly, even though we know much better bounds, but it's clear that you can bound these by, let's say, 2 to the 2n, right? 4 to the n. it's very clear that cannot go any larger than this because this is the number. And this can be written as 4 to the n. So assuming z, let's say, is larger than, I believe, 4, the series is convergent, at least for these z's. Or, oh, 2, right, because there's 2n also there. Okay, now for expressing a generating function, this has the looks because of the something minus square root has the looks of a solution to a quadratic equation. So what I want to do is to express a quadratic equation of this g of z. Okay, what I want to do is to find a way to write, let's say, 4 g of z, a g of z plus a g of z squared plus b g of z plus c equals 0 in some way, such that I can derive, I can solve this equation and derive this formula. And this can be done directly from the definition and the recursive relation shown here. Okay, this can be done, and I'll refer when I forgot to publish the notes today, but I'll publish it just as we finish. This can be done directly from the definition. And I'll write where is it in the book. That's not what I want to do. What I want to do is do something a little bit different and hint to something that's called the symbolic method. And using the symbolic method, we'll be able to get this function in this form easily without writing any infinite sums. Okay. I'll write one infinite sum. Okay, so the idea for the solution is first look at the generating function of this sequence, which I'll denote as sum n goes from 0 to infinity of Cn z to the n. And okay, this is a generating function. We've seen generating functions before. And just by this definition, it's clear that if I have a solution for C, I have a solution for G. Right? Because I can write g of z as 1 over z c of 1 over z squared. Something is over. Okay, so it's enough to solve this. And this I want to write a little bit differently. And for doing so, I will pick one example from here, and it will be the same example we solved before. So instead of writing the Catalan numbers as the coefficients and then z to the n, I want to sum over all binary trees T. I want to sum over z to this number, the count of t, and I think of count of t as the number of internal nodes in T. Okay, and why are these the same? Because if, let's say C5 is the number of binary trees with 5 internal nodes, then there will be 5 trees such that z to the 5 occurs here. Okay, so these two are the same. This is a very specific case of something that's called the symbolic method, but I'm doing just one instance. Now you can notice that, as we've seen, there's, for example, one tree with 0 internal nodes and one tree with internal node and so on. And we can use the same procedure we've done before and think, if we look at a particular tree T, we can think of Z to the T, the hashtag T, as one Z that will represent one node that's the internal node here. We have C, the number of nodes in TA, times Z. Let's write it down. Let's maybe do one more step. The number of nodes in T is 1 plus the number of nodes in TA plus the number of nodes in TB. Right, this is just by definition. And this can be also written as Z times Z to the TA, Z to the TB. And this can be done for any tree T. I did not assume anything about either T or TA or TB. What I only assume here is that there's at least one internal node. So I need to separate the count for the empty tree, with the tree with only one leaf. And this tells me that this summation can be written as, so there's no restriction on this one, and there's no restriction on this one. So I can write down the same sum as 1, representing this case, which I excluded, times Z times C of Z squared. Squared because one instance for this part and one instance for that. Again, this equals C of Z. And for now, I only treated this sequence as like a formal power series in Z. I did not say anything about Z being a number that I need to get large enough, okay, that later. But now I have a quadratic equation in C, which I can just solve, right? Any question about this derivation? It was
how to use like the last one. And why is this like C12?
Okay, because I didn't put any restriction about A. There are all the options for create the first one, and there are all the options. So you want to write down. I'm not maybe doing all the application for writing the power series this way, but the idea is that I can generate any.
Or you could take like any TA and any TB, and this would construct a single T.
Exactly. Yeah. So there's for any option for TA and TB, I will construct one.
Exactly one.
Exactly one. Yeah. Okay, now I just need to solve this equation. And this would be, so I'll just rewrite it in a way that it's easier to do. So it's Z square root of Z minus C of Z plus 1 and 0. And then it's just like, applying the formula. So I'll skip this one.
So like a real thing, so that
Yes, okay. So this is for the formal power series in Z. This would be actually there are two solutions, and I need to pick one of them, but it will be the one that will make sense. And then I can say, okay, for Z large enough, I know that this series convergence, and And since this equation has to hold at some point, it will hold at any point that it converges. Okay, maybe this can be done a little cleaner, but I want to jump to a generalization of the Catalan numbers. So the next question is, and I'll keep going with the trees examples. What if instead of binary trees, I'll talk about ternary. Ternary, that's the three-array trees. Be sure that I'm recording. Okay, so now every node has 3 children. How would I express the exactly 3?
So each one you can partition T like TA, TB, T.
Exactly.
Solve
Oh, no, let's not talk about the generating function, just the numbers, right? Just the recurrence relation.
so you need to choose like I, J, and K, so the sum is and
Right, exactly. So what I need to do in general is to write, this time it will be Tn equals sum over all the options of A, B, and C, so that the A plus B plus C equals n minus 1. Then write it down as there equal n, and this is n plus 1. And in this instance, I want to take again same manner A and B, C. Right, this will be the same. And if I want to do it more generally and write here, say, PRE trees, just to use some standard notation for this problem, then for the PRE trees, I have the numbers going as P Fuss-Catalan number. Fuss-Catalan numbers. And for this, we'll have, let's say, n or n plus 1 in the notes. N plus 1. This would equal sum over that's A1 up to AP, such that there's some like AI equals N. This is a generalization of this. So here I have some 3 equal N. Here I have P as a parameter, and I have their product. This is a generalization for AI. Okay, so this is just a generalization for the Catalan numbers, but okay, so I generalized one of those, and you may ask whether a similar generalization occurs for other combinatorial problems that we're trying to solve with the Catalan numbers. And the answer is yes, but it's not always the intuitive one. Okay, I put a few examples in the homework for what are the generalizations, for some generalizations relevant, but it's not immediate. In particular, notice that here the case that p equals 2, so Cn, the regular Catalan numbers, are the Fuss-Catalan numbers with parameter 2. Okay, and this is like, if I wrote this generally for p arbitrary, then binary is just p equals 2. And it turns out that this can be solved as well to get a closed formula. And the formula is, and this we will not do, 1 over Tn plus 1 times Tn plus 1, which is n. And notice that if you put 2 instead of p, you get a formula that's slightly different than this one, but it's actually the same. So this one can be written, this is a more known formula, but can be written as 1 plus 1. And these numbers, the Catalan numbers and Fuss-Catalan numbers, occur in sometimes surprising occasions, and usually and also writing from a few of these problems, writing down a bijection between them is maybe not impossible, but very not intuitive. But the connection between them is the recurrence relation, either the regular one or the. Okay. Questions about this Catalan or this Catalan? Okay. So in the remaining 10 minutes, as promised, I talk a little bit about free groups and about failures. So I want to write down two definitions. One is of the free group with generators set S, finite set, let's say 1, okay? And later on, I'll bring product of. So the free group is a set of generators. The only thing that matters here is the number k. These are just symbols that they can place. I mean, in terms of the properties of it. It's just the set. First of all, it is a group, but I need to prove that claim that it is indeed a group. It's the set of all sequences AI, A1, A2 up to n, where n is any number, and all the AIs are either in S or in what I denote as S inverse, where S inverse is just symbolically writing the inverses of these elements. So for example, if S equals Y, then the words X, X, Y, and X, X inverse Y, and X, X inverse, X inverse, Y inverse are all in the in this set, okay, because I can take any one of those or their inverses. However, I have one additional definition, which is what is the reduced word. every such word. And the reduced word just means that whenever I have a pair which is either for any so whenever I have any S in S, every occurrence of S inverse or S inverse S, I can just remove. Okay, so I say, so stating this differently is saying that, for example, this word I can call W equals the word Y because I was able to reduce this prefix here, and it's easy to see that the reduction of a word is always a process that terminates and it yields a unique result. Okay, so this is the free group with the particular set of generators. And see if there was anything else I would say about it.
So this is the step.
Oh, right. Okay. There are a few more things I needed to say. So, yeah, what is the group operation? So, the operation is just concatenation. And you can either write concatenation and reducing, or you can just say concatenation and treat two words with the same reduced word as the same one. Okay, so and so there is this operation, and can be proved that there is an inverse under this operation, and the identity element is the FT word. Concatenated to any element, and it does not change. Okay, so this is a group.
Just want to change the utility is ABC, ABC.
And I wrote down the several properties of this group. For example, that don't call all of them, but one of them is that okay, never mind. It's not really crucial for the and the other definition I wanted to show is of free product of groups, which it has to do with this definition, but it's slightly different. So here, except for this property that through an element and its inverse can be just taken off of it. This is the only relation, non-trivial relation we have in this group, other than just like except for the translation word to the reduced word, there's nothing else that can be said except for like if you look at two reduced word, if they look differently, they are. Given two groups, let's say G1 and G2, I can define something that's called the free product G1 and G2. And this will equal all the elements of the form, let's write them as in H. All the elements of the form G1, H1, G2, H2, so on, such that all elements are denoted by GR. G and H are H. But here, except for the concatenation and reduction, I also have the whatever was the structure of G and H. Okay, so for example, in the case that take G to be Z2 set with just two elements, let's say 0 and 1, and H to be Z3, the additive group modulo 3. Then if I take, let's say, so we know that in this group 1 plus 1 plus 1 equals 0, right? It was the identity element of this group. So if I, in this notation, if I call this one, say this is the identity of H, and this is H1, and this is H2. So in this notation, if I write, concatenate, and do not write here also the option to write H is included here. Just start with the identity element, identity element can be removed. So in this case, if I concatenate, let's say, call this EG G. So if I write the element GH1 and I concatenate it with H1 and with H1 again, here, because of this relation, this will yield again the element G. Although I did not explicitly write the, symbolically write the inverse of H1. So this is like a difference between this notation and that one. So this is the free product groups. And it can be proven that this is a group as well. Maybe associativity is not easy, I don't always but it is indeed group, and not the definition we need for it.
So how do you do the reduction? Only the elements, the identity element, then you can reduce, maybe reduce the what?
Exactly. So in this instance, you either get, yes, the only way to reduce is if you have something from the same group to cancel. There's no like non-trivial relation elements, G and elements.
The only existence relation that is important. What we should do is the group structure. More this be
Yeah, I want to stand.
that's the origin of the name, right?
Yeah, so the term freeness comes from the idea that, I mean, we haven't seen the definition of freeness yet in our context, but it's the idea of no non-trivial relations. So here I think of the free product of G and H as like, I do have the structure of G, I do have the structure of H, for example, here. But I do not assume any, and there's not only I don't assume, there's no any non-trivial relation between elements from G and elements H, and then I can think of the groups G and H as being in some sense free of each other. But this hasn't been formalized.